everyone, we're going to be going over chapter 2.4, which is the average rate of change of a function. So we're going to learn how to find the rate at which values of a function change, as like the input variable changes, and then the average rate of change between any 2 points. We're going to discover that it's actually the slope of the line containing the 2 points. So let's look at this example. So you might already know that distance traveled is like a function of time, and then you have your formula for speed. So like speed is distance over time. So that's similar to like average rate of change becoming the slope. So in this example, we could calculate the average speed from 1 to 4 p.m. So our x-axis is the time, and then the y-axis is the speed in our graph. So we could calculate time. So if it's from 4 to 1, we do 4 minus 1, which is just 3. And then to find our distance, at 4 o'clock, we traveled 200 miles, and then at 1 o'clock, we traveled 50 miles. So we do 200 minus 50 is 150. So that's going to be our average speed. So really the formula is s of 4 minus s of 1, meaning like what the distance was at 1 and 4, minus over 4 minus 1. So we get 200 minus 50, which is the distance, over time, which is 4 minus 1. So it's 3. So we get 150 miles over 3 hours is 50 miles an hour. So that's from 1 to 4. And then from 2 to 3, our average speed is going to be s of 3 minus s of 2, or what the distance was at those points of time, over 3 minus 2. So s of 3 is 140, and s of 2 is 75. So we do 140 minus 75 over 1 is 65 miles an hour. So that's average rate of change using like the speed formula, which actually becomes the slope of the line containing those points. So for an actual formal definition of what it is, we're going to have a f of a and then b f of b, which just means the function at b, at the point b, which is like our y value, and then f of a is like the y value, be distinct points on the graph of the function f. The average rate of change between a and b, x equals a and x equals b, is f of b minus f of a over b minus a, or delta y over delta x. So the delta is the triangle, and that just means change in. So we're basically doing the change in the y values at a and b over b minus a. So it's like change in y over the change in the x. So the average rate of change is the slope of the secant line between x equals b and x equals a on the graph of f, which is the line that passes through those 2 points. So here in this graph, this is like a picture of, I guess, what's going on when you're doing the average rate of change. So we have f of a f of a here, and then b f of b, and then the secant line, we're finding the slope. And remember, the slope is the rise over run. So our rise is the difference between f of b and f of a, and the run is the difference between b and a. So we're just finding the slope of that secant line that connects those points, and that's going to be our average rate of change. Okay, so for this example, we have f of x equals x squared, and we want to find the average rate of change in 2 cases. We have a and b here. So let's do a first. So we have x1 equals 0 and x2 equals 1. So I want to, this is like our formula, right, for average rate of change. We have x of 2 minus fx of 1 over x2 minus x1. So that's going to be f of 1 minus f of 0 over 1 minus 0. And usually it's going to be the x2 is going to be greater than the x1, so that's how I know to do the 1 first. So whichever one you have first here, you basically just have to be consistent. So if you have the 1 first here, then you need to do f of 1 there. If you have the 0 second, you need to do f of 0 second. I usually just do whichever one's larger. Oops. I list first here in the denominator rather than the 0, just because it comes out nicer and you don't get negatives as often. So I just do that. So I get 1 squared, because our function is x squared minus 0 squared over 1, which is just 1. And as we can see here, that's going to be the average rate of change for our graph. So our slope, or our function is this x squared here. So it's just a parabola. And then I'm finding the difference between when x1 is 0. So when x1 is 0, we have 0. And when x2 is 1, that's like our second x value. That's the 0.11. And so I'm finding the secant line, or the slope of that line connecting those 2 points, is going to be 1. And that slope is greater than 0. All right, now let's do part B. So I have x1 equals negative 2 to x2 equals 0. So as you can see, I did f of 0 first because the point 0 is greater than negative 2. So I did f of 0 minus f of negative 2 over 0 minus negative 2. So don't forget that's minus on the bottom, and then we have a negative 2, which is why I had the parentheses so I don't forget a minus sign in these two cases. Okay, so 0 squared is 0, and then negative 2 squared is 4. So I'm subtracting those. So I have 0 minus 4 over 2, which is negative 2. So that's saying that the difference between when x1 equals negative 2, our graph is at 4, and then when x2 is 0. So the secant line connecting those points has a negative slope because our slope is negative 2. So it's less than 0. Okay, for our next example, we're looking at the distance an object is dropped is given by the function in terms of time t. So I have dt equals 16t squared, and we want to find the average rate of change over these various intervals. So I have from 1 second to 5 seconds. So I'm going to do d of 5 minus d of 1 over 5 minus 1. So I get 16 5 squared because I'm plugging in 5 into my function. So like the t is time, and so I'm plugging in the 5 because it's 5 seconds. So if I plug in 5 to your equation, it's 16 5 squared minus 16 1 squared over 5 minus 1, which you get 96 feet per second. Okay, so part B. Here we don't have numbers anymore. We actually have variables, but it works the same way, or we could do the same thing. Okay, so I have a plus h and then a. So a plus h is going to be greater than a because it's a plus an h. So that h is going to be positive, so it's going to be greater. So I'm listing that one first. So I have d of a plus h minus d of a over a plus h minus a. So we're going to do the exact same thing. Just act like these variables are actually numbers from what we did from part A. So part A, we knew what to do. We do the exact same thing for part B, just treating our variables as numbers. So I'm going to plug in the a plus h like where our 5 was. So I have 16. a plus h is our whole variable. So this is like our whole t. So I have 16a plus h squared minus 16a. Okay, so now I'm going to find out, and this is all over a plus h minus a. So I'm going to multiply out a plus h, make that nicer. So a plus h squared equals a plus h times a plus h. So if I multiply that out, that's going to be a squared plus ah plus plus h squared. So that's going to be a squared plus 2ah plus h squared minus a squared, because what I'm going to do here is I had all that multiplied out. Oh, this is supposed to be a squared. Okay, so I have all this from the first term and then this from the second term, and then I just factored out the 16. And so I factored out the 16, and then I get 16a squared plus 2ah plus h squared minus a squared. And I could cancel the a squareds, so I get 16 2ah plus h squared over h. I could factor out h now. I get 16h over 2a plus h, because we still have h left over because it's squared. And then I could cancel the h from the numerator and then the denominator. And then I'm left with 16 times 2a plus h. So actually in part B, what we calculated was the difference quotient, which you'll learn more about in calculus, but it's used to calculate instant rates of change. So here we did a little preview where the average rate of change over that interval was actually the instant rate of change over that interval. But all you need to know is basically how to get the difference quotient, not really knowing like the instant rate of change or anything like that. So we're able to do that. Alright, and it's good to note that if a function is increasing on an interval, then the average rate of change between any 2 points is going to be positive. And then if a function is decreasing, then the average rate of change between any 2 points is going to be negative. So that's pretty intuitive, right? So if the function is decreasing, then obviously the rate of change is going to be like negative because you're decreasing, you're taking away. And then if it's increasing, it's going to be positive because you're adding things to it. Okay, so this is going to be an example. It's from your textbook, and it does the time and temperature. So I want to know what the average rate of change between the 4 to 7 p.m. And then here I just listed those specific temperature values that they had in the book. The table is a lot bigger, but I just want to look at 4 to 7 just to talk about that. Because it's a little bit different since we're dealing with time. So I have f of 19 minus f of 16 over 19 minus 16, because the way that the problem is worded in the book, it's hours since midnight for 7 p.m. And then, so since midnight, there's 19 hours to get to 7 p.m. So I guess it's military time. And then 16 for 4 p.m. after midnight. So that's how this problem is just like set up, and I just wanted to clarify that. And it's 51 minus 64 over 3, which is approximately 4.3 Fahrenheit, or negative 4.3 Fahrenheit actually. So the temperature drop is represented by a negative because the temperature is decreasing. Okay, and then I wanted to note that as we've learned that the average rate of change is like slope, I want you guys to notice that linear functions have a constant rate of change, right? Because the average rate of change of a linear function or a line between 2 points, that's the slope. And our slope is constant, right? We have linear functions have a constant rate of change. We have the same slope for our function. The slope doesn't change. So, like, for example, we know for this function, our slope is 3, and that doesn't change, right? It's the slope of that line is always going to be 3. So in order to see that, we're just going to go through, pretend that we didn't know that. So I'm going to see what the average rate of change between 1 and 0 is. So I have f of 1 minus f of 0 over 1 minus 0. So that's, we're plugging in 1 for x. So I have 3 times 1 minus 5 minus 3 times 0 minus 5. I get negative 2 minus negative 5 over 1. That's 3. So yeah, that matches our slope. So the same thing for part B. I have f of 7 minus f of 3 over 7 minus 3. That's 16 minus 4 over 4 equals 3. So yep, that matches the slope. And here I'm going to do the difference quotient again. So part C of this problem, doing the difference quotient, that proves that the average rate of change is always going to be 3 because it's like arbitrary values that we're plugging in and not specific examples or specific numbers. So now we're going to go ahead and prove that the average rate of change is always going to be 3. So I have f of a plus h minus f of a over a plus h minus a. So remember, our a plus h is going to be like our x value. So I plug it in. So I have 3 a plus h minus 5 minus 3a minus 5 over h. And then I distribute the 3, multiply it out. I get 3a plus 3h minus 5. And then distribute the negative. You get 3a negative 3a because you're distributing. And then negative 5 is going to be positive 5. So I get negative 3a plus 5 over h. Things cancel, and I get 3h over h. The h's cancel, and I get 3. So C actually proves that our average rate of change is always going to be 3. Okay, so that's it for this video. So I'll see you guys next time.